Hello, I'm Mike McCulloch. Today I'd like to talk to you about how uncertainty can save physics, and indeed it can. So the uncertainty principle is well known. It was devised by Heisenberg over 100 years ago. And it looks like this. So this means that the delta P there on the left is the uncertainty momentum, and the delta X just next to it is the uncertainty in position. And the principle states that this must be greater than some small number, which is h bar over 2, h being the Planck constant, and h bar being that divided by 2 pi. So this is Heisenberg's uncertainty principle, and you can derive quantized inertia very easily from this, and thereby predict galaxy rotations and all the other things that predicts. So here we have an illustration of a Planck mass, which is the square box in the center. And let's imagine it's accelerating to the right, which is shown by the twin arrow underneath it. And you'll see behind it a Rindle horizon, so that's to the left. That horizon exists because information can't catch up with the object because it's accelerating to the right. And then on the right, there'll be the Hubble horizon, or the cosmic horizon, which is a horizon very far away, but at which point everything's moving away from the object at the speed of light, so information can never get to the object from that direction either, from a very far distance. So here you can see that on the plot, I've drawn the uncertainty in momentum with two different arrows pointing left and right. It's quite clear from this plot that the uncertainty in position on the right-hand side, to the right of the Planck mass, is huge because the distance from it to the cosmic horizon is big. So we can say that there the uncertainty in position is massive. So dx is massive there. But on the other side, the uncertainty in position is smaller because the Rindle horizon is closer to the object. So on the right-hand side, we have a very large dx. So by Heisenberg's uncertainty principle, you'd expect a very small uncertainty momentum, and then on the left-hand side we have a small dx, so we would expect a much larger uncertainty momentum. So thinking about this intuitively, you would expect there to be a quantum jitter on average pushing the object back against its acceleration towards the Rindle horizon, because the uncertainty momentum is greater on that side of the object. And I'll show that mathematically now. So we can work out dx on both sides, the uncertainty in position. So on the right-hand side, it's theta over 2, where theta is the cosmic diameter. And on the left, it's c squared over a, where a is the acceleration of the object and c is the speed of light. So using Heisenberg's uncertainty principle, we can then put this into an expression for the uncertainty in momentum. So the momentum on the left-hand side will be h bar over 2 times c squared over a, and on the right-hand side the uncertainty momentum will be 2 times the reduced Planck's constant divided by the cosmic diameter. Okay, so you note that the new thing here is that we're assuming that dx in Heisenberg's uncertainty principle relates to horizons. The horizons are defining dx, which is a characteristic of quantized inertia. Okay, so the force is given by the differential of momentum with time. So that's dp by dx times dx by dt, and dx by dt we can assume is the speed of light because information travels at the speed of light. So if you put a finite difference, if you like, for the momentum, the delta p's, we have that the force is equal to c times the delta p on the left minus the delta p on the right, divided by the distance between the two halves of the Planck mass, which is going to be the Planck distance divided by 2. And then if you put the values we had before in for the delta p's in this formula, you get this formula, which should start to look very familiar. This is looking very much like the quantized inertia formula. And then So this is equivalent to F equals ma. And so what is the mass? And we get this for the expression for the mass, which is exactly the same as a quantized inertia one for a Planck mass. So in this way, we've derived quantized inertia from the uncertainty principle extremely simply, and this expression, of course, this modification to mass solves the galaxy rotation problem and the wide binary orbit problem and Proxima's orbit problem, and also these lab tests that have been done. It agrees with them too. So this is very nice. So uncertainty saves physics, and it does in another way as well, because if you go on dogmatically believing in the old textbooks, then you're not going to make much progress. But if you have some uncertainty about the old physics, then you might be persuaded to engage in progress. And I think this is definite progress. Okay, so I hope you've enjoyed this short and it wasn't too mathematical. Please do support me at Patreon if you can, and I look forward to seeing you next time. Goodbye.